Hello, we are going to look at question 4 from 2011, exam 2, it's a VCAR exam. It has this nice pulley question. So the diagram below shows particles of mass 3 kilograms or 2 kilograms on adjoining smooth planes with an inclination, that's an angle, theta, and 2 theta respectively. Okay, so there's theta, and over here's 2 theta. Okay, now theta's in degrees, and it's greater than 0. So the masses are connected by a light, inextensible string passing over a smooth pulley. So that little bit of information helps you to come to the conclusion that the tension in the string is constant, they're the same. Okay. And the tension in the string T, newtons, and the acceleration is going up the plane. Alright, so up the plane of the 3 kilogram mass. So that way is your acceleration. Now, how are we going to approach this? Well, there's our acceleration. First, let's consider that some kind of frame of reference. The frame of reference is essentially the directions that we're going to take for the I component and the J component. Okay. Now, when you look at these problems, it's sometimes easy to break it down to the I component being the part that is parallel to motion, and your J component would be the part that is perpendicular to motion. Alright, now we've got two particles that are going that undergo motion in different directions. So it's okay to have two different reference frames of reference for our two different masses. So we can have a parallel and a perpendicular part of motion for our 3 kilogram mass in that direction, because we're moving up the plane, so it's just good convention to have positive I going up the plane in the same direction as motion. And then, because they're attached via this light inextensible string passing over a smooth pulley, we'll have the accelerations of the two blocks being identical. So this acceleration is the same as that acceleration. And because the accelerations are the same, they're equal, then we find out that it doesn't matter that we can have two different frames of reference. It's more convenient to have two different frames of reference for our formulation of our equations of motion. But it's not going to have an impact on our final result for acceleration. Okay, because we know the acceleration of the two masses are equivalent. Okay, so establishing frames of reference like that, we're going to now write down equations of motion, that is, the sum of forces acting on the blocks. We've got two forces there, tension in the string, and a weight force pulling down the 3 kilogram block. Now there's also a normal force pulling back up. Now normal force is important when you're looking at friction, but at the moment we have smooth planes. The information there is saying we've got smooth planes, so not that important at the moment. And then we have forces on the 2 kilogram block, the tension and the normal reaction force. Okay, and we've got a weight force, 2 kilograms, pulling it down. Okay, now looking at the first 3 kilogram mass, there's our equation of motion. So T, newtons, for tension, up in the direction of motion, so it has positive sign. For the same with a positive 3A, we must have a positive tension because they're both going in the same direction. And then the component of the weight force is pulling it back down the slope, so it's negative. Okay. And it's important to note that our two tensions here tension 1 and tension 2 that are drawn, well, they're actually the same tension. And it's because we have this important idea that they're connected by this light inextensible string passing over a smooth pulley that results in both tensions being equivalent. Okay, now let's focus on what's going on here. We've got we're about to write for part B the equation of motion for the 2 kilogram block. So I've broken the components of our 2G into one that's parallel to motion and the other one here perpendicular to motion, and we've got a geometrical construct here of a right angle triangle with now how does that relate to this angle, this 2 theta? Well, let's look a bit closer. Here we have, here's the weight force. If we extend this down, it's going to come perpendicular to the base. Okay? And that's what we've see here. There's the weight force coming down perpendicular to the base, and that's the corner of the slope. And we know here is 2 theta. Now, just using some triangle geometry, we know that this angle up in the corner has to be 90 degrees or pi on 2 minus 2 theta. Okay, got that? Now, let's extend that and relate it to the right angle triangle here of the components of the weight force. Okay, so extending the ramp going up, and I extended the weight force, and now this part here, that's the parallel component of the weight force. And what I notice is I've got a parallel component of the weight force there, and I've got the plane, and they're parallel lines. And I'm going to use some nice parallel line geometry to find out some other angles in this little construction. So this angle here is opposite to that angle, so that must be 90 degrees minus 2 pi. Now, what about the alternate angle over here? Okay, because it's an alternate angle, this angle there and that angle there, they are equivalent, and so this angle must be pi on 2 minus 2 theta. Okay, and that's really good because now I know my angle here in the inside, a little acute angle there of my right angle triangle. Okay, and I get this for the component of my weight force that is parallel to its motion. That is this side. That's this red vector here. That's the adjacent side to the angle. That's inside here. Okay, so angle being pi on 2, take 2 pi. And then I subtract the tension, go in the opposite direction, and that's 2 times the acceleration. Okay, now I'm going to use some rule on the symmetry of circular functions to express this in another way. Okay, when we subtract from 90 degrees or pi on 2, we get the complement of the function, and so it's just sine of 2 theta, some sine of the small angle. And there we have it. There's our 2 equations of motion. Marvelous. Let's look at the next part. Alright, show that the acceleration is this expression. So let's start with our 2 rules, and what we're going to do is add them together. Okay, and by adding them together, we eliminate the tension. Okay, so this is solving the 2 equations simultaneously using an elimination method, and we're eliminating the tension force. And we obtain this expression, and the 2a plus 3a gives us a 5a. Now, I know a trig identity, a double angle formula for sine of 2 theta. There it is, and we're going to apply this one. And I get it in this form. There it is. My 2 theta becomes 2 times sine theta times cos theta. And now I've got 2 terms, that term and that term, with a common factor of sine theta. So let's factorize that out with also a common factor of the g. And what's left is There it is, 4 cos minus 3. And that's equal to the right hand side 5a. And transposing 4a, we get our expression. And part D now gets us to find the angle for the system to be in equilibrium. Now that means it is stationary, it's not moving, and so the acceleration must be 0. So we let a is equal to 0, using that expression, 4a, and there it is. Okay, now what do we notice about this expression? It's a factor times another factor, and that is equal to 0. So using a null factor theorem, I can make each and equate them to 0. So the first one was sine theta is equal to 0. Well, that happens at angle equals 0, or angle equals 180, but we're told at the start that theta must be greater than 0. So we can't just destroy our plane and make it flat. So this one is not going to be very helpful for our inclined plane problem. We're going to use the second one. And we're going to equate that to 0. And just transposing, we get theta equals inverse of 3/4. And on the cas, we get 41.4 degrees to the nearest tenth of a degree. Marvelous. Okay. Now consider a changed situation where theta is a fixed value of 30 degrees and the plane supporting the 3 kilogram mass is made rough. So that means it has friction now. So that the coefficient of friction between 3 kilogram and the plane is 5/100ths. Okay, now the plane supporting the 2 kilogram mass remains smooth. So on that side of the plane for the 2 kilogram mass, it's no friction. Find the acceleration of the 3 kilogram mass up the plane. Correct to 1 decimal place. Alright. Acceleration of the 3 kilogram mass up the plane. So we're going to use our equations of motion that we established before. But this time we're going to include here it is, there's the friction force. And because we're moving up the plane, we're subtracting the friction force. That's going down the plane in the same direction as the weight force. There's the weight force. Okay, now the tension's still there. The tension's the pulling force up the plane. And that's 3 times the acceleration. So, from that, I also need to consider the second equation of motion for the 2 kilogram block. This one doesn't experience any friction. Okay, and so it's the same equation of motion as before. So using those two, what am I going to do with them? Well, I'm going to eliminate the tension again by adding the two equations. And by simplifying a little bit, there's the two when I evaluate the sines and the coses, and then adding them together, it gives me this for 5a. Okay, and there's the common factor of g there that I've taken out. And then I evaluate that expression in the calculator, and I get 0.2 meters per second squared for the acceleration up the plane. Now the last part, for the changed situation, the system will be in equilibrium if the 2 kilogram mass is replaced by another mass called m, and m has some range. It's got a minimum value, m1, it's got a maximum value, m2. Right, so there's kind of a range of possible masses for there to be in equilibrium. So you essentially have got a situation where you can allow a maximum mass and a minimum mass. So you have to think mass is equal to mass is equivalent to force. Okay, so force equals mass times acceleration. So if you've got a minimum mass, you're going to have a minimum force. And if you've got a maximum mass, you're going to have a maximum force. So two situations where one's a minimum force and one's a maximum force. So looking at our equations of motion on the 3 kilogram mass, there we have it. And the equation of motion on the 2 kilogram mass, but now we're not using our mass of 2 kilograms, we're going to use capital M. Okay, now by adding them together we obtain this expression here. Okay, and because we're in equilibrium, the acceleration is 0. Okay, following that? Now, this is the situation where the friction is acting down the plane. Okay, so that helps the weight force to pull it back down. And the only thing that might be pulling it up in the other direction is the tension force, and that's linked to the weight force of the other mass, the 2 kilogram mass. All right. Now, what about if we consider the other example when you've got a friction force acting in the other direction? So we've got the weight force of the 3 kilograms pulling it down, but now the friction force, there it is, that's plus now, that's acting up, that's pulling it up as well. Okay, so that means this is a situation where the block has a tendency to want to move down the plane. The 3 kilogram block wants to move down the plane, whereas the previous equation, this one here, this equation is for situation where there's the tendency for the 3 kilogram mass to move up the plane. Okay, so two different directions of motion in that situation you've got to consider. There are your two cases of limiting equilibrium. Okay, in this kind of problem, limiting equilibrium problem, you've got to consider two possibilities. All right, and you do it just by changing the direction of the friction force. Now, from equation number 1, when we evaluate the equation and transpose and solve for M, we will get that value. Okay, now that's a maximum. And then we do the same for the equation number 2, and we evaluate it and transpose for M. We will get that value. So there's your two, that's your range for mass. Okay, that mass is allowed to be within those two values in kilograms, and the system will still stay at equilibrium. Interesting concept. Okay, well, that's how we go through that problem. Hope that was helpful, and we will try another one.